This piece of aluminum starts as a block, a solid, featureless brick of alloy. By the time it leaves Apple's manufacturing chain, it will have been milled, anodized, polished, and fitted with components that took years to design, and it will be 5.1 millimeters thin. Today, we are going inside the iPad Pro. Not just the specs, the actual engineering decisions, the trade-offs, the obsession that goes into building the world's most powerful thin computer. Aerospace-grade aluminum, 661T6, is the starting point. Apple's engineers demand more than a good-looking shell. They need a body that shrugs off bending, twisting, and years of daily abuse, all at just 5.1 millimeters thick. That's why the iPad Pro's enclosure is milled from a single solid billet. No seams, no welds, no weak points. 5-axis CNC machines carve out the entire form in one continuous sequence, shaving the block down with micron-level precision. Each pass is calculated to avoid internal defects, leaving a chassis that meets a flatness tolerance of just plus or minus 0.05 millimeters, which is less than the width of a human hair. But thin metal alone is not enough. Internal ribs, just 0.6 millimeters thick and spaced every 8 millimeters, are cut directly into the shell. These hidden reinforcements boost torsional rigidity by about 18%, letting the iPad Pro resist flexing even under stress. Every opening, camera, speaker, and Thunderbolt port is machined with tolerances as tight as plus or minus 0.05 millimeters. Around the antenna slots, laser-cut windows allow wireless signals to pass, but only after finite element analysis pinpoints stress hotspots and confirms the shell can survive drops, twists, and impacts. The final result is a unibody with a measured elastic modulus of 71 gigapascals, able to withstand both accidental knocks and the relentless pressure of thinness. Every gram shaved from the chassis is a calculated risk, balanced by simulation, testing, and the relentless pursuit of durability in a form factor that pushes the limits of what aluminum can do. Packing a full desktop-class computer into a 5.1 millimeter chassis demands more than clever cooling or tight assembly. It requires a system brain that can deliver top-tier performance without ever crossing the thermal line. The M4 chip, built by TSMC on the enhanced 3-nanometer N3E process, is the answer to that challenge. With 28 billion transistors compressed into a die smaller than a postage stamp, the M4 brings together CPU, GPU, memory controller, and a dedicated neural engine, all in one slab of silicon. This density is not just about raw speed, it is about efficiency. The 3-nanometer node packs transistors 53% tighter than the previous generation, letting Apple run more logic at lower voltages. That means less heat, less wasted power, and more room for everything else. Early N3E yields hovered around 65%, but process refinements, like improved EUV mask alignment and chemical-mechanical polishing, have pushed yields to over 80%, making mass production possible for a device this thin. Unified memory is a cornerstone. Instead of separate memory pools for CPU and GPU, the M4's architecture lets every processing block tap into the same pool at up to 112 gigabytes per second. The result is no bottlenecks when moving massive images, video, or AI workloads. The neural engine stands out, delivering up to 30 trillion operations per second while sipping just 0.6 watts. That is 5 times the efficiency of running the same job on the CPU. Real-time augmented reality, handwriting recognition, and on device A, all run without draining the battery or overheating the shell. Packing this much compute into such a slim profile is not just a flex. It is the only way to balance Apple's design ambitions with the realities of heat, power, and space. Every transistor, every memory channel, Every watt is calculated to make thinness practical, not just possible. Two organic light-emitting layers, stacked in tandem, form the centerpiece of the iPad Pro's display. This dual-stack architecture is not just for show, it is the technical backbone behind the screen's ability to hit 1,000 nits of sustained brightness and a searing 1,600 nits peak in high dynamic range. One layer handles everyday tasks, optimized for color accuracy and efficiency. When the system detects high dynamic range content or demanding graphics, the second layer activates, unleashing the full 1,600 nit punch without burning out the organic materials. Both layers are bonded with a transparent conductive adhesive, keeping the total thickness to just 6.5 microns, critical for fitting inside a 5.1 millimeter chassis. But brightness is only part of the equation. Apple's engineers built in ProMotion, a variable refresh system that adapts between 1 and 120 Hz. Reading a document, the screen drops to 1 Hz, saving power and extending OLED lifespan. Drawing or gaming, it ramps up to 120 Hz for maximum fluidity. This is not just about smoothness, it is about balancing energy demands against battery constraints forced by the thin enclosure. Every panel is factory calibrated, measured with a spectrophotometer to ensure a delta E of 1.5 or less. That is professional grade color, consistent from unit to unit. The result is a display that meets the needs of creative pros while staying within the harsh limits set by thinness and battery physics. Every millimeter shaved from the iPad Pro's profile comes at a cost. Battery capacity drops from 40.88 watt-hours in the previous generation to just 38.9 watt-hours in the M4 model, a 4.8% reduction. That translates directly into less room for energy storage, even as the display grows brighter and the silicon gets hungrier during peak workloads. To compensate, Apple's power management engineers turn to aggressive chip-level gating. When the system idles, the M4 can drop core voltages as low as 0.4 volts, shutting down unused GPU units and putting the neural engine into deep sleep. The result, idle draw for the entire USB 4 port falls below 0.1 watt. Every microwatt saved is a chance to stretch battery life back toward the 10-hour mark users expect. But the pursuit of thinness means something else goes missing. Gone is the 3.5 millimeter headphone jack. No SD card slot, only a single USB 4 port remains, a move driven by both spatial constraints and the need to reinforce the chassis around any opening. Internal debates between industrial designers and hardware engineers, documented in Apple's own review meetings, landed on a single, reinforced port, sealed tight for water resistance and structural integrity. The trade? Simplicity, but at the price of flexibility. The iPad Pro's form is uncompromising. Its function is shaped by what could fit and what had to be left behind. Inside Foxconn's Zhengzhou campus and Pegatron's Shenzhen facility, the iPad Pro's journey from precision-milled shell to finished device unfolds at a scale and rigor few factories can match. Each unibody arrives from CNC milling and anodizing, but before a single screw is turned, dimensional checks begin. Coordinate measuring machines probe every surface, verifying flatness and wall thickness to within plus or minus 0.02 millimeters. Any deviation, even a hair's breadth, sends the part back for rework. Only shells that pass this first gate move on. Assembly flows in tightly choreographed cells. Teams install the M4 logic board, battery, and tandem OLED panel into the aluminum chassis, slotting each piece into its designated cavity. Every step is tracked. At key stations, automated torque tools record fastener data, while laser scanners confirm part alignment. Before the Thunderbolt port is cleared for final fit, A robot cycles a plug in and out 1,000 times, checking for microfractures or play. Failures trigger immediate teardown and root cause analysis, no exceptions. Endurance matters just as much as precision. Ports must survive years of daily use. Displays must remain bonded, free of dust or trapped air. Only after passing these gauntlets does each unit advance to final assembly and packaging. The result? A device whose tolerances and durability are not marketing claims, but measured outcomes, verified on the line, one iPad at a time. Stress testing isn't an afterthought, it's the final judge. In Apple's root cause labs, technicians push the iPad Pro beyond the limits of ordinary use, hunting for failure before customers ever touch the device. Every finished unit faces a gauntlet of environmental and mechanical abuse. Packaging is dropped from 18 inches in 3 orientations, following ISTA 3A protocols. Only units that show 0 functional loss and less than 400 microns of chassis deformation pass. Surface roughness is scrutinized by laser microscope. RA must not exceed 0.3 microns, or the shell risks premature wear and anodized delamination. Temperature cycling is relentless. Each device endures swings from -20 to +60 degrees Celsius. This thermal stress exposes microfractures, solder fatigue, or adhesive failures that could appear months down the line. Antenna windows are retested after every drop and cycle, confirming that S parameters stay below -30 decibels for uncompromised wireless performance. Failures are dissected on the spot, with root causes traced to process drift, supplier variation, or packaging flaws. Only after passing this battery of tests do engineers sign off. The result? A device engineered not just for launch day perfection, but for years of real-world survival. Every millimeter shaved, every watt saved, is the result of deliberate engineering sacrifice. The real price of ultra-thin power isn't just in materials. It is in the invisible trade-offs Apple makes at scale. What are we really paying for? The specs, the feel, or the philosophy? Comment below if you want a deeper dive. Subscribe for more.